Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Bamdu Lim with us today. Hey, Bamdu.
Hi, everyone. Nice to meet you.
Nice. Nice. Thank you very much for being willing to talk about your article.
Thank you. Thank you for inviting me and picking our paper.
It's a lovely one, and we'll get to that very shortly. Bamdu, where are you located at?
I'm in Suwon, in South Korea. This city is 40 kilometer away from capital Seoul, to south. So I'm in now my office. I'm working as a research professor at Kyunghee University.
Very cool. Very cool. Let's see, North Korea, if I remember my latitudes right. Well, we've gone past equinox. So is it fall yet in South Korea? Is there snow on the ground yet?
Oh, it is actually fall, but I feel like winter is coming. So the temperature abruptly drops nowadays due to the cool air from the north.
Ah, right. So it's October 20th, at least in my time zone. I believe it's Thursday, October 21 in your time zone, as we're doing this. And yeah, it's definitely gotten a little bit cooler. I'm in Phoenix, Arizona, and we've turned the corner, so we're definitely in fall. Although by most people's reckoning, we're still pretty hot. Most people would call it we do hot. For us, it's just warm. So yeah, we got a little ways before winter hits, but very cool. Bamdu, what do you like to do for research?
I'm interested in the formation process and the evolution of young stellar systems, particularly stellar associations. Cool. The stellar associations are the collections of stellar clusters or the stellar group and isolated stars spread over several tens of parsecs.
Okay.
This large stellar system even form a larger structure, the so-called star-forming complexes, along the galactic spiral arms. So therefore, they are not only the essential building block of the galactic spiral arms, but also the useful target to study the star formation process on different spatial scale from the few parsec to several hundred parsec. However, the detailed study of this large stellar system were very limited in the past because of difficulties in the evaluation of the membership of stars scattered over a large area. Yeah. So now the Gaia mission opened a new window to select the genuine members and study their properties in detail. So I'm now very happy to survey the lovely galactic stellar association with new data.
Cool. And that is going to bring us to this very lovely AJ article, a kinematic perspective on the formation process of the stellar groups in the Rosette Nebula. And Bamdu, take us away.
Thank you. First of all, I would like to thank our co-authors for working together and helping me a lot. Especially 3 graduate students who were involved in our paper. Okay. They are great handling the radio data and analyzing spectra. 2 of them found a postdoc position last year and this year, so now they are working very hard. So, and the other student will be a PhD candidate in this semester. I will sincerely keep my finger crossed for him and 2 young postdocs.
There we go.
Yeah. So,
okay.
Yeah, our team has surveyed several galactic stellar associations to understand their formation process in the point of view of stellar kinematics using the Gaia proper motions and radial velocities obtained from high-resolution spectroscopy.
Okay.
This is the part of a series of the surveyed work. The target is the young stars in Rosette Nebula. Now, this is a famous astronomical object.
It is.
Yeah, the first section introduced the theoretical and observational background. So I would like to briefly introduce the background.
Yes, please.
Yeah, there are 3 theoretical models explaining the formation of stellar associations. The first model postulates that stellar association may result from the expansion of stellar clusters after undergoing rapid gas expulsion due to stellar feedback.
Okay.
The second model explains that stellar associations may result from multiple star formation events taking place along filamentary structures in a turbulent cloud on a very short time scale. In the third model, the feedback from massive stars can compress the remaining gas. And then the next generation of stars can be formed in the compressed gas. So yes, push the remaining gas. So this self-propagating star formation can result in the stellar associations. However, many observed properties of stellar associations could not be explained by one specific model. So our hypothesis is that the stellar associations may form through the mixture of two or three processes proposed by the theoretical models.
Okay.
So in this context, the largest star-forming region is the ideal target to test our hypothesis because this star-forming region is highly substructured. Some of the stellar groups seem to be associated with the remaining gas. Also, the membership of the young stars has been well evaluated using the multiwavelength data from X-ray to infrared in many previous studies. The section two describes the data we used. Since the young stellar system are in general distributed along galactic plane, so a large number of field stars are observed together in the same field of view. So we had to carefully select the genuine members to obtain reliable results. So we first built a list of member candidates from many published data.
Okay.
Yeah, early type stars may be probable members because of their short lifetime, such as OMB type stars. So we compiled OB star list from many databases of MK classification from website. We also gathered the catalogs of infrared sources such as Spitzer and Orwise, and the Chandra X-ray sources from previous studies, and classify them into young stellar objects candidate, as shown in the appendix, and X-ray emitting star candidates. So we then cross-matched the list of the member candidate to the catalog of Gaia early data lead 3. But here we use the Gaia TR2 photometry to use the empirical extinction law. Please move to the figure 1.
Figure 1, yes.
Here, the left panel shows the color magnitude diagram of stars in the surveyed region. The blue dots are early type stars, a red triangle, green square, and light blue open scale represent class 1, class 2, and young stellar object candidate with transitional disk respectively, and crosses are the X-ray emitting star candidate. The most of the candidates are found within the specific locus outlined by the solid line. So
what are the gray dots again?
Gray dot is the all stars in the surveyed region, the 1 degree region.
Got it.
Yeah.
I'm with you.
Okay. So only consider the stars within the locus as member candidates. And we took a high resolution spectra of more than 300 young stellar objects candidate and ionized gas over the Rosen Nebula using a multi-object spectrograph hectoshell on the 6.5 meter MMT telescope. So in the right panel, the small open circle you see, that shows the position of hectoshell fibers. So we can take more than 200 high resolution spectra of ionized gas by one exposure. from this observation, we can construct a data cube, like a 1-degree field IFU data. So we can construct the 3-dimensional structure of the ionized gas. So I will gonna show you it later.
Okay. Nice.
We also obtained the 12CO120 and 13CO120 data cube from the professor Mark Heyer. So I would like to thank him again here. In section 3, this section we address we address the scheme of the final membership. So in my opinion, this part is practically the most important part in this paper.
Yeah.
According to conventional wisdom, the young stars formed in same molecular cloud are at the same distance and have similar kinematic properties. So please go to the figure 2.
Yes.
Yeah, the left panel shows the distribution of Gaia parallaxes of the probable members and the associated errors. So although we only use the member candidate, there are a number of non-members in our list. So we only consider the stars between 1 and 2 kiloparsec, given the previously determined the distance of 1.5 kiloparsec.
Yes. Okay.
In right panel, this panel shows the distributions of proper motion of probable members between 1 and 2 kiloparsec. There is a strong concentration that then must be related to the genuine members. So we selected the stars with proper motions within the 3.5 times the standard deviation from the mean proper motions as the genuine members.
Okay.
Again, we calculate the mean and standard deviation using these stars. And this procedure was repeated until the statistics converges to constant value. Okay. Finally, we selected 403 members in total, as shown by the red symbols in both panels. I anticipate that more members will be able to be identified with the final release of Gaia data or the future mission or follow-up observations.
Okay. Okay.
Yeah. Please go to figure 4, the next figure.
Yes.
Figure 3. Yes. The upper panel shows the color magnitude diagram of genuine members, so we can see the clear sequence of young stars. Yeah, but we exclude one star that's marked by the open circle because this star is fainter than the other stars at given the color. So membership of this star should be checked with the final release of Gaia data.
Okay.
We exclude these stars in our study.
Okay.
The lower panel shows the distributions of distance and the radial velocities of the final members. Yeah, from this figure, we determine the distance to this rosette region to be 1.4 plus or minus 0.1 kiloparsec, and the systemic radial velocity of 13.4 kilometers per second at the local standard of last.
Okay. Cool.
Okay. Yeah. We present our all findings in section 4, so it would be interesting. So please go to the figure 4.
Yes, I will. Nice big table there. A list of members. Here we go. Some of them.
Yeah. A list member. You can use it.
This is not all 403. It's the first 10.
Yeah.
Okay. Figure 4.
Yeah, the left panel. So we plot the spatial distribution of members on the optical DSS LED imaging. The gray scales are the beautiful Rosette Nebula. And the stellar number density map is shown in the right panel. The solid and dotted and dashed lines represent 70%, 50%, and 8% of maximum stellar density.
Okay.
So we can see there are 4 stellar groups. The young open cluster, you know this cluster. this cluster, the cluster NGC 2244 is occupies in the center of the Larger Nebula. This is the most populous group in this region. We also identified 3 more small stellar groups at the border of H2 bubble.
Okay.
As shown by the outlined by the boxes in the both panel. The 2 of which have been reported in previous studies, the NGC 2237 at the northwestern patch of the nebula and the PLO2 at the southeastern ridge. The stellar group in group B was the newly identified this here. The interesting thing is that this group is located at the tip of gas pillar. The pillar is facing toward the NGC 2244. So I thought that there must be interesting things. So I'm going to show it later.
Okay.
So the left panel, so color-coded solid lines represent the proper motion vectors of individual stars relative to the systemic motion of NGC 2244.
Okay.
And the different color indicates the different position angles of the proper motion vectors. The stars in the NGC 2244 tend to show outward motion. And some of the other stellar group also shows systematic motion towards specific direction, while the other one shows does not show such a systemic motion. So I will deal with this in later.
Okay, I'm with you.
Okay.
Yeah.
And we investigated the basic parameters of the NGC 2244, such as the radius, total mass, and ages, something like that, because this cluster is the most populous in this region, and so it has a huge impact on surroundings. Also, their properties could give us a clue to understanding the cluster formation evolution. So first, the median coordinates of stars within the most crowded region was adopted as a center of the cluster, as shown by the cross in the right panel of figure 4. Yep. Yes. And then we fit the Elson's density profile to the observed density profile fit in figure 5. Okay. Yeah. From this figure, a radius of 11 Archimedes was at the dashed line. The 11 Archimedes was adopted as an apparent cluster radius. The C also, please go up to the figure 4.
I'm sorry. Put them both up
there. Yeah, we can see the first figure for comparison. See the solid line, the open circle in the left panel of figure 4. That is the apparent the cluster radii. The region over this radius can be contaminated by the member of 22 and NGC 2237.
Okay. Yeah.
So we consider only stars within the apparent cluster radius as the cluster member.
Yeah.
So please go to figure 6. Okay. The figure 6 shows the color magnitude diagram of NGC 2244. All symbols are same as at figure 1. The multiple sets of mixed groups isochrones are plotted on this diagram for different ages, 2 and 3, 5, and 10 million years. Yeah. From this figure, we obtain the parameters of individual stars and clustered parameters. So the luminosity of main sequence turn-on, from pre-main sequence to the main sequence, the main sequence turn-on luminosity is very sensitive to the age of a cluster. So the main sequence turn-on age of this cluster is about 2 to 3 million years.
Okay.
Yeah, we also infer the masses of individual stars by interpolating the Gaia BP minus RP colors and RP magnitudes to those of the missed ice crons laden by the mean extinction.
Right. I'm with you. Yep.
Yeah. And then we derived the present day mass function as shown in figure 7.
Nice. Figure 7. Awesome.
Yeah. Yeah, this is the present day mass function. Yeah. The amount of mass loss of the most massive stars in this cluster is very small in first 2 million years. So this present mass function can be considered as initial mass function. And then we constrain the slope gamma of this mass function using the least squared method. As a result, the mass function is consistent with the Kroppa and Salpeter's initial mass function within error.
Okay. All right.
Okay. The total cluster mass was estimated to be about 879 solar masses. Okay. By summing the masses of individual stars with masses larger than 1 solar mass, and by integrating this mass function that was extrapolated to Kroppa's initial mass function down to the hydrogen burning limit.
Okay. 0.07 or so.
Yeah, and then finally we obtain the half mass radius of this cluster as 2.4 parsec from the radial mass distribution.
Okay.
So now we are ready to see the internal kinematics and the dynamical state of this cluster.
Yes.
Now we are ready. Okay, so we could see the outward motion of stars in NGC 2244, but we wanted to more quantitatively show the cluster expansion. So we calculate the vectorial angle of individual stars, where the vectorial angle is an angle between the position vector from cluster center and the relative proper motion vector of a given star.
Yes.
So the vectorial angle of 0 degree means our star is radially escaping from cluster center.
Yes.
Yeah. So in figure 8.
Yep. Very cool. Okay.
Yeah. This figure shows the vectorial angle distribution with respect to the projected central distance. The dashed line denotes the half mass radius. A number of stars tend to have the vectorial angles close to 0 degrees. To highlight this result, we present the histograms in the right side panel.
Okay.
Yeah, the red symbol obtained from all the cluster members clearly show a peak at 0 degrees.
Yes.
Which indicative of the cluster expansion. Also, the blue histogram was obtained from the only stars within half mass radius.
Okay.
The peak at the 0 degrees appears weaker than that of red histogram. It implies that the escaping stars, stars escaping from the cluster center, is mostly distributed over the half mass radius.
Yes.
On the other hand, I was curious if young star clusters are rotating because it could provide important constraints on the cluster formation. So an arbitrary axis passing through the cluster center was considered. We then computed the mean radial velocities of stars belonging to each side, separated by the axis.
Okay.
And the difference between the mean radial velocities between the two sides.
Okay.
So this computation was repeated for the different position angles of the axis.
Okay.
So if the difference between the mean radial velocities between the two sides for different position angles of axis appears as a sinusoid curve. That is the signature of cluster rotation. So please go to figure 9.
All right. And yeah, okay, there's your projections. And oh, there we go, figure 9.
Yeah. The left panel is that signature. So NGC 2244 is rotating. Turned out to be rotating. In the curve, the half the amplitude of the sinusoid curve corresponds to the projected rotational velocities. So the projected rotation velocities is about 0.7 kilometer per second within a radius of 6.5 arcminute. We also found interesting things is that the projected rotation velocities vary with the radial distance of the clusters, as shown in the middle panel. In the middle panel, so cluster rotation is rapidly increased within the half mass radius, in which the cluster mass also rapidly increase. Over this half mass radius, the cluster rotation slow down, as shown in this figure. Yeah, we also see the signature of the cluster can be easily seen in the velocity map in the right side panel.
Okay, mean radial velocity, yes.
Yes, the eastern part of the cluster is receding away from us, and the western part of the cluster is approaching to us.
Okay, yep.
Yeah, our findings suggest that the NGC 2244 might have formed in a rotating cloud or collisions of gas clumps. So I recommend the readers report to section 5 for detailed discussions on cluster formation. It would be interesting.
Right, very cool.
Yeah. Okay. And now we have all the parameters of the cluster, such as the half mass radius, the total mass, and the structure parameters estimated from the SS profile fit. So now we can infer the dynamical state of this cluster in comparison of the virial velocity dispersion with the observed velocity dispersion. So please go to the equation 4.
I'm sorry, what figure?
Equation 4.
Equation 4, gotcha. Yep.
Bottom of this page.
Yes.
Yeah, the velocity, the virial velocity dispersion calculated from this equation 4 is about 0.6 kilometer per second. Please keep this number in mind.
I will.
Please go to the next figure, figure 10. Figure 10, next page. Yeah, the upper panel shows the distributions of tangential velocities along right ascension, declination, and the radial velocities, respectively. Yes. The blue histogram. We obtained observed velocity dispersions from the best fit Gaussian width, as shown by the red curve. Yeah. However, the velocity dispersions contains the contribution of measurement error. So we need to subtract the contribution of error. So in the lower panel shows the distributions of associated measurement errors. So we obtained the intrinsic velocity dispersions after quadratic subtraction of mean errors. So we present the final intrinsic velocity dispersions in the table 3.
Table 3.
Yeah, just below this figure. Yeah, the last column. The last column shows the intrinsic velocity dispersions along each axis and radial velocities.
Yes.
The average intrinsic velocities was adopted as one-dimensional velocity dispersion. So this value is about 0.8 kilometer per second, which is much larger than the virial velocity dispersion of 0.6 kilometer per second. So this cluster is at the supervisual state and gravitationally unbounded.
Okay, good.
Yeah. Yeah.
Yep.
We were so curious that this cluster is mass segregated or not. So we probed the signature of dynamical mass segregation. To see these features, we plot the figure 11.
Okay.
Yes. Yeah, in upper panel, this panel shows the relation between the projected central distances and the two-dimensional tangential velocities. The size of the dots proportional to the stellar mass. Okay. So as you can see, we could not see any strong central concentration of massive stars. So in lower panel, this figure shows the relation between the stellar masses and tangential velocities. The black dots on the solid line represents the mean and standard deviations of the stellar masses and tangential velocities within the given mass bin.
Okay.
But also, we could not see any strong correlation between two quantities. So if this cluster had experienced the mass segregation, the velocity dispersion should increase with stellar masses. So these two figures telling us the NGC 2244 was not mass segregated. So this is the natural result given the relaxation time of 80 million years, okay, which is much larger than the age of this cluster. And now, so shall we move our attention to the stellar groups around NGC 2244? So we found these three stellar groups at the border of NGC, at the border of H2 bubble. So we speculated that some of these groups must be formed by feedback from massive stars. So I thought that the remaining gas is now receding away from the ionizing sources and compressed by them. So if some stellar group were indeed formed by feedback from massive stars in NGC 2244, they will be receding away from the cluster.
Yeah.
That was the idea to uncover the formation process of these stellar groups. Please go to figure 12.
Yes. Good.
Yeah. Figure 12 shows the three-dimensional position velocity diagram and two-dimensional position velocity diagram along the right ascension and declination respectively.
Yes.
Red and blue spheres represent the member of NGC 2244 and the other stellar group's members respectively. And bluish cloud in left panel and color-coded the contour in the middle and right panel shows the distributions of ionized gas traced by nitrogen 2 emission line at 6584 angstrom. I love this figure because this figure gives me imagination of a three-dimensional structure.
Right. Yeah, it's very good. Very nice figure.
Yeah, I have actually animation too, but I regret to I did not submit the animation to the journal.
Next.
Okay. Yeah, as we saw, the NGC 2244 is located at the cavity of H2 bubble. While the positions and radial velocities of the other group members well overlap the distribution of ionized gas. So it indicates that the star and gas in the same physical system. So, and then we probe the physical association between the remaining gas and the stellar group in detail using radio data. Please go to figure 13. We plot the members of each group on the integrated intensity map obtained from 12 CO data, the grayscale.
Okay.
The size of the red symbols is proportional to the brightness of individual stars. The arrows denote the propagation vectors to individual stars relative to the systemic motion of NGC 2244.
Okay.
The plus symbol shows the positions of fibers that were used in spectroscopic observations of ionized gas.
Yeah.
We also present the position velocity diagrams of each group in the bottom and right side panel each. And in the position velocity diagram, the dashed line shows the systemic radial velocities of NGC 2244. So this is the guideline.
Yes.
So we can see the velocity of ionized gas, marked by plus symbol. Red follows the velocity field of molecular cloud, the grayscale. Among the three stellar groups, only the group in the region B in the middle panel shows kinematic properties that can be expected from feedback-driven star formation. The members of this group is systematically receding away from cluster center to southeast, and their radial velocities are very close to those of the remaining gas in the position velocity diagram.
Okay.
In addition to this, in only this group, low mass class 1 object that is on the earliest evolutionary stage of protostar was identified, which is indicative of younger age than the other groups, possibly. So the formation of this group might have formed triggered by the massive feedback from massive stars in NGC 2244. On the other hand, the other two groups, NGC 2237 in the left panel and PLO2 in right panel, do not show such receding motion from the clusters.
Right.
Yeah, in the left panel.
Yep.
Left panel. Yeah, the members of NGC 2237 tend to move towards the south, not the northwest.
Yeah.
And their radial velocities are different from the cometary, the gas clumps moving at 2 or 3 kilometers per second.
Okay.
In the right panel, the members of PLO2, please go to the right panel. Yes, thank you. Yeah, the members of this group shows somewhat random motion rather than the systemic motions toward the specific direction. Their radial velocity is close to that of NGC 2244 in the position velocity diagram, but their physical association with the adjacent gas structure is unclear due to the large scatter of the radial velocity. So we concluded that these two groups might have formed spontaneously at the current position.
Okay.
So in conclusion, young stellar population in Large Nebula might have formed through the three different processes proposed by the geological models as our hypothesis. Basically, the multiple star formation events might took place along the filamental structure in turbulent cloud. The most populous cluster NGC 2244 might formed in the high density and rotating clump, or the filamental hub, or the collided clumps. As a result, now the cluster is observed to be rotating. As time goes on, this cluster is now expanding, so a number of the members are escaping from the cluster. On the other hand, NGC 2237 and PLO2 might have formed spontaneously at current position as a result of the multiple star forming events, while the stellar feedback from the NGC 2244 might trigger the formation of a new generation of stars at the southeastern pillar. Okay. So that's the main result of our paper.
Very nice. Very nice. Very nice. Bamdu, I want to thank you very much for walking us through your very lovely AJ article. So let me ask. let's go ahead and take a future look. Let's say over the next 5 years or so. Could, for example, where should we go? So are there other nebulas where one can do this analysis? Is there enough data there to do this same analysis on other types of or nebula? Are there perhaps plans to increase the membership of these clusters in the Rosette Nebula? Are there additional theoretical calculations that could be done? Just kind of where do we go over the next 5 years?
We continue to survey the stellar association. So we have a plan to analyze the young stars in the same manner. So we will uncover the common formation process of stellar associations in 2 or 3 years.
Oh, cool. Okay.
Yeah. So actually, since the Gaia data release, a large number of studies have discovered not only the new stellar associations and stellar clusters or substructures in the previously known stellar associations. They have studied their properties in detail. So the next step is to find the signature of star formation from the structural feature and kinematic properties of stars and stellar group in comparison with those of molecular cloud.
Ooh, okay. Mm-hmm.
Yeah, our group and the other research teams have already initiated this work. So we are getting closer to understanding the star formation, star formation process. But what we see now is the features like fossil after onset of star formation. So there is still missing link in conversion from gas to stars.
Okay.
In my personal interest is how the angular momenta of a molecular cloud redistributed to the cluster rotation, binary orbit, and rotation of individual stars.
Yep.
So in next 5 years, we need to fill this gap in our knowledge in collaboration with many astronomers who have expertise at different wavelength observation and computer simulation, because we need to study the different phase of star formation and on different spatial scale.
Cool. Very good. Very good. Well, I look forward to seeing some of your future papers on this topic, particularly in the angular momentum redistribution. That would be very nice. Very nice. Bamdu, I want to thank you once again for walking us through your very lovely article.
Yeah, thank you for inviting me and pick our paper.
It's always beautiful. And that'll do, everyone. And I hope this makes your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.